Yeah, thank you. Yes, welcome back from lunch. So I will try to finish up my little series of lectures on approximation algorithms inspired by FPT methodology, especially kernelization. And I will return once more to our good old friend, vertex cover. But say in contrast to what most people look into, I will focus on graphs of bounded average degree. So why that? I think, at least, I mean, Fedor mentioned this book on sparsity in graphs. Well, bounded average degree is a very simple kind of model in a certain sense to try to say that a graph is not too, well, thick somehow. And in fact, many more or less realistic graphs do have something like bounded average degree, at least far more than do have bounded degree. Although I would claim that there are far more algorithms around or people around who care about bounded degree graphs as opposed to bounded average degree graphs. Furthermore, if it comes to practical thingies like testing algorithms, I will show you several of these in the following as well. It's very easy to generate random instances here, because you have this nice upper bound on the number of edges. I mean, that's what you basically use, and then you can fairly easily generate these kind of graphs. And so that's all good, but there are also many pitfalls around these average degree bounded graphs, as I will soon explain. But maybe just as a starter, I'd like to work with you through a very simple example, sorry, namely through this graph. So this is not a very big graph, honestly, but this is always the problem. If you start trying to show more realistic graphs with 100,000 vertices, then things become very messy on the screen. So bear with me to take this simple example. But this example is, of course, a bit designed to show different rules which we can apply. And I try to highlight them a bit with these boxes. So, and everybody who is kind of familiar with vertex cover, I didn't bother to explain or define this problem at all, will notice the very first rule that I try to apply there, the degree 1 rule, right? Or if you want to be more generous, something like folding, like ground rule. Here, this guy must be sort of in a, or should be in a minimum vertex cover. So it's kind of an exact rule to, well, what is this rule telling me now if I don't look at parameters? So basically it tells me to remove this piece of the graph, so these two vertices and these two edges, and continue. And it is fairly easy to construct or reconstruct the solution of the original graph once I found the solution of the rest of the graph. That's fine. There is something about credits here at the end. I will come to that later. Okay, so this is one rule. There's something else, like here we have even two subsequent degree 2 vertices. We can fold them, and basically it means I have to throw them out together with the incident edges, and I connect this 11 and 5 vertex, which unfortunately is not on the slide here. But anyways, think about this being here. The next thing is to find this little triangle here, and because we've previously deleted this hair dangling down here. So this has become a degree 2 vertex. So really this is an zigzag rule again. I take these 2 vertices into the cover. At least this is what I want to do. And continue. Well, there are more triangles like that. I say here something like triangle situations may propagate. Do you understand what I mean with this propagation? So where are more triangles in this graph? Well, for instance, down here. Here is a triangle with a degree 2 vertex in it. So if I now take these 2 vertices in the cover, then all of a sudden this becomes a vertex of degree 1. So this means that number 19 should be in the cover. So all of this disappears. So altogether 5 vertices and 8 edges will disappear. And finally up there, okay, there's another special situation. Namely, here we have a degree 3 vertex that satisfies this funny inclusion property in terms of neighborhoods. By the way, who is U here in this example? Just to get you with me. So if this is V here, who is U? Sorry, maybe it's, sorry? Maybe it's too small, so sorry. It's just this guy here, the 21. So this rule is a rule that you can find, for instance, in Ulrike's PhD. So if you really want to look up these degree 3 rules and similar things. So we can basically take this into the cover, and all of a sudden we have another degree 2 triangle here, so we can continue. This will fire actually again a degree 1 rule, and in the end of the day, this guy will remain some k4 times k4, and I just say it's easy to solve. Well, at least you can continue a little bit also with rules to get this exactly solved. So if I trace back, I will arrive at this Pepper solution. This is a solution for this k4 times k4, and the other things are basically by our rules putting them back. I claim this is off by at most 1. I mean, from some optimal solution. Where did we play possibly wrong, in a sense that we have only an approximate thingy here? I mean, most of the rules that I applied were exact rules, apart from one case, actually. Yeah, the exact. So this triangle here, here we applied this kind of approximate rule. Excuse me? The neighbor rule. No. I was too quick at that. I must add here this one. Here, this here. If I take these 3 into the cover, then, well, I only know that 2 of them must be there. So that's why I'm off by 1. Of course, it might be also optimum. And I would claim at least that you don't see immediately if this is an optimum solution or not. I mean, this is just the beauty of this NP problems. You simply don't see immediately if this is the best you can do. But in fact, as we will see, there are better solutions. So this off by 1 is a real thingy. Anyways, it's pretty close. At least off by 1. If we have a big graph and we have a solution which is just off by 1, it's not that bad. And everything we did is polytime. So that's, of course, the point. So we cannot expect to be exact every time. Otherwise, well, you know what happened. So, okay. So I was telling you already. Ah, yeah, by the way, here's an optimum solution. So just playing with the capacitance there. And if you compare them, it's exactly this place here where we shuffle around things plus shuffling around things here in order to make it happen. So both have to be done, otherwise, yeah, it wouldn't fit together. So I used many rules that you know of, maybe some of them which are not that well known, so the degree 0, degree 1, okay, we know this. But if we are aiming at a factor alpha approximation for average degree bounded graphs, that's what we are after now, degree 1 is a dangerous rule. It's an exact rule, but it's dangerous. Why? Well, because generally speaking, we will increase the average degree in that case. And I will really play with the fact that I have bounded average degree in order to prove the correctness of my algorithm that I will show finally. So that's crucial, that this is not violated. And this rule will violate this condition in at least usual circumstances. So maybe we have to be a bit more cautious if we apply reduction rules in order to obtain some approximative solutions only. So maybe put another way, deleting low degree vertices in general, not just degree 1 vertices. They may destroy a given upper bound on the average degree of a graph. Why? Well, because I'm deleting too few edges, right? If I want to maintain a certain average degree upper bound, I have to maintain a certain ratio between edges and vertices. So this is now where this banking business comes into play. And I think Elvira also had something with banking business, but the other way around. She had a savings account, right, in some of her examples. I have a debit account. So, which means that when working with low degree vertices, which I will actually process first for several reasons, the most important being that I know of all these nice exact rules that I want to apply to them. So if I want to deal with these low degree vertices, then I will have to take some credit from my bank. And this credit has to be paid back when processing vertices of higher degree. Why? Because I want to maintain the invariant, sort of, that certain nice structural properties are true, so that I can apply certain things. If I have a sort of bank account of 0, so basically no credit taken, then I should have this average degree constraint maintained. Otherwise, I'm not so much caring about it, put it this way. And working this way, I can somehow relax this funny upper bound on this average degree condition. As I said, I need this in order to prove the correctness of my algorithm. Maybe I should emphasize for each and every case. But if my reduction rules, which are in themselves correct, say, yeah, if they finally get rid of all the edges, I just forget about this banking business. I mean, I'm happy because I have resolved the graph more or less to optimum. So this banking business is only for the case when I have to argue why I should be in the position to apply more of these reduction rules in the end of the day. Okay, so just to understand this banking business a bit better, it's a very simple observation, what's stated here as lemma 1. If I have a graph with average degree, say df, and if I delete x vertices, say, and at least the average over 2 times x edges, then the remaining graph will maintain my average degree upper bound. As I said, that's a very simple thingy, if you think about it for 2 secs. What does it mean in my case? Well, what's my case actually? I never told you. I will tell you now. I want to deal with graphs of average degree at most 4, and also I want to have a minimum degree of at least 2. So my original graph wouldn't fit into this. But for those graphs, I can find a factor 1.5 approximation for vertex cover. And actually, this isn't beating things that has been published before. So it's not just sort of a nice playground, but this is improving on earlier work of bounded average degree. And so what I have to deal with is, of course, now 2 things in order to really make it work. I have to maintain the approximation ratio, and I have to meet or maintain this degree constraints. So, and in order to maintain this degree constraints in a certain way, I need my bank. So maybe coming back to this little lemma, what does it mean in my case? It means in my case that whenever I delete x vertices from my graph, I would have to delete twice as many edges at least in order to maintain the average degree. That's coming out of this formula. Well, and if I don't do this, I have to go to my bank and ask for money. So that's exactly where this whole thing comes from. So even if I now, just for curiosity, apply it to a case which does not really fit into this theorem, then, okay, in this case, I would have the following thingy. I take 2 vertices out of my graph, and I'm deleting 2 edges. But I should delete at least 4 edges. So somehow I need a credit of 2. That's this 2 edges which I take from my bank, sort of. And similarly, with this folding rule, I delete 2 edges, so it looks like 3 edges. As I said, I didn't draw the 3rd one here now in this next slide. But I'm deleting 2 vertices, so 2 edges credit. What's here? So I'm deleting here 3 edges and 3 vertices and how many edges? I'm deleting 3 edges in the triangle, these 2 edges connecting to 4 and 2, and then this other edge that I didn't draw is also now deleted, so therefore in the following it doesn't matter. So I'm really deleting 6 edges for 3 vertices, and that's fine. So I don't need any credit, but I also cannot pay back at this point. So what about this propagation thingy? What did I say? I delete 5 vertices and 8 edges. So 2 edges are missing, I need a credit here. And in this case, I'm taking out 1 vertex only and delete 4 incident edges. So I would actually only need 2 of them for my constraint. So now I can start paying back some part of my credit to the bank. Okay, and so Here, I even didn't bother to count, so more to count here. Anyways, so in the end of the day, we have to look back at our rules and see what they mean in terms of our banking business and also in terms of our approximation ratio. So these are X-side rules. This is very nice for this purpose, but often enough they are bad with banking business, so they need to take some credit. And this slide actually shows already how we might be able to overcome these problems with the banking, at least for this funny average degree of 4, which is actually a bit special, I must admit, but anyways. So you might know this triangle rule. This triangle rule, if I really want to, or if I really have a triangle where I don't have any degree 2 vertex, then first of all, it's not hard to observe that I will automatically delete at least 6 edges if I take out all 3 vertices. So for the bank, this is fine. I either don't need any credit, but possibly I can even pay back something. But on the downside, say this is an approximate rule. So I don't know, in general, if I have a triangle, if I really need to take all 3 vertices into my cover, but I need to take 2 of them at least. So therefore, this little pictures are read this way that, well, 2 of them are for sure, say, and 1 is, well, some additional thing that worsens my approximation ratio a bit, but okay, at least the banking business is okay. And the next example, kind of a degree 3 rule, for approximative purposes, already tells a bit how this banking business works after all and in the end. Because I don't really need to apply this, as we will see, but I will do it occasionally. But the point is the following. So assume we have this type of situation. So I have a degree 3 vertex. For the general case, there is no real good reduction rule, but I can do it approximatively as follows. Assume I first grab this edge and put both vertices into my cover. Of course, this is not nice. It's just factor 2 locally, right? I mean, I have to take one of the 2 in my cover, that's for sure. But like the local ratio argument, of course, I don't know if I need both. But having done this, what does it mean? I deleted these 2 vertices plus all incident edges. So this means this vertex in the middle down here has become a degree 2 vertex, so I can fold it afterwards. So therefore, altogether, I will arrive at this picture basically. So this is gone, but this is just telling you, okay, we have these 2 vertices removed and basically apply the reduction rule. So it means I have 1 more vertex in my cover. So altogether, I've put 3 vertices into my approximate cover, while 2 of them are for sure. So this is again a 1.5 approximation like this. That's fine. And on top, if I count edges. So the folding rule in itself is not that nice, maybe. It's not that nice because in general, I would just lose these 2 edges and 2 vertices. So that's not very good. I have to take a credit. But because this is degree 3, I lose 1 more edge here, first of all. And then if the surrounds are not too bad, put it this way, because I've dealt with small degree vertices already, then it's not hard to see that altogether I'm removing sufficiently many edges with this rule to keep my bounds. Okay, so, but these are these technical things which come up here, which are kind of new if you look to it only, or if you know this only from the classical FPT background. You don't have to care about this otherwise. So, this is maybe a bit bad of a slide, but I will go slowly through it. So, I will try to maintain this funny min degree constraint, like minimum degree of 2, by using this degree 1 rule only implicitly, and making sure that this never hurts too much in terms of banking business. Then there's some notion which okay, I should have mentioned this. So this is basically part of a paper together with Liana Brankovic that we wrote actually some time ago, and that was on really FPT approximation of vertex cover. But there was some part which we never presented, which I'm presenting now. That was on polytime thingies, and so this is basically the part of it. And there we introduced this notion of a worsening step, which has also other names in other papers. If you look for papers in from other people, there are different names for that. But the basic idea is, if I have an exact rule that, in our case, is taking credit from the bank because these degree constraints are not met, right? Then it is always possible at some later point of time, not immediately as I did here, so here I did it immediately, but to grab some edge, best an edge which has many, where the two vertices have high degree, or at least one of them has high degree. So that by removing these two vertices plus all incident edges, I can pay as much back to my bank as I like. Okay? And this, of course, worsens, and therefore this name, worsens my approximation ratio deliberately. But what I do with this is basically trying to maintain this average degree upper bound thingy. Okay, if you really want to do more details, then the next paragraph is something like that. If I put p vertices into the cover due to, say, exact reduction rules, and if this finally reduces the number of vertices in my graph by q, and the total number of edges by r, then we have some freedom to apply these worsening steps. Namely, I could pick p pairs of adjacent vertices or p edges, right? And in such a way, and that's of course what we have to show that this is possible, unless if we run out of applying reduction rules, yeah. So such that we will have or can remove this many edges. And if we can do so, and that's what we have to show, of course, then we are fine, because we can always either do some reduction steps, or if we can't, then we know that we can do worsening steps, which try to go back to our degree constraints, so that finally we can apply again reduction rules. Because doing worsening steps changes the graph, so we have new possibilities to apply reduction rules. That's the gist of it. And just to make it concrete again, for a degree 1 rule, if I put this leaf neighbor into the cover, then, and this leaf neighbor has degree 4, say, then I'm already fine for my case, because I remove 4 edges, so even this type of degree 1 rules is fine. But if it's, say, only of degree 2, as it was in our example previously, then I have to take 2 edges sort of credit from my bank. And as I showed you, somehow these things balance out. Okay, so what I have to show and what I won't show to you, but this really is some pages in the journal paper. So rules are always applicable if the bank is empty, or, well, otherwise the bank is non-empty, so we can apply worsening steps. And we do this simple thingy as long as possible, and so this basically gives you already the idea of the algorithm. Maybe coming once more back to this famous folding rule, which is displayed here again, in case you don't recall. So in general, we remove 2 vertices and 2 edges, which is not sufficient to maintain our degree bounds, so we have to take a credit of 2. And if we do appropriate worsening steps, so we will have removed sufficiently many edges and vertices finally, and so that's fine. And here's this way of compensating things. Here we have the folding rule. Here later we apply this rule, and altogether that's already balancing out in terms of degrees. Okay, so we're doing this processing from low degree to high degree vertices, as I said, taking credit from the bank if necessary. These high degree rules are then basically only trying to do the worsening steps, right? But recall, we don't have a sharp maximum upper bound, but this average degree bound. So in general, we will have really high degree vertices, but these are really nice for these worsening steps because they allow us to take out lots of vertices, edges with 2 vertices. So that's why this whole story works in the end of the day. So finally, there are 2 ways to leave this algorithm. So either we get up to the point where this graph has minimum degree 4 plus, and the bank is empty. And this means, the bank is empty means we have an average degree of at most 4 and a minimum degree of 4. So this graph is 4 regular, right? So, putting things together. So then I can go shopping in my favorite algorithms shop and see, okay, there are very nice algorithm for d-regular graphs, which are doing the job then. Or I leave the algorithm where the bank is still having some money to be paid back. Well, in that case, it means the graph has no edges any longer, so I don't care about the bank. It's going bankrupt, who cares? But I have found a solution which is better than promised. That's actually also told by still having a credit from the bank, because I use exact rules. They are better than the approximate one, obviously. So I will show you some results, at least, of experiments. So we really ran this on thousands and thousands of random graphs. Actually, this was a bachelor thesis of Florian. And, well, just as a test bed, if we have average degree 2, then we can solve all graphs optimally. But if you think about this for 2 secs, it's clear that it must be the case. The rules are like that. Okay, fine. A bit more surprising is that we never found any example of an average degree 2.5 graph randomly constructed, where this algorithm doesn't solve to optimality. This is just kind of experimental evidence at the moment that this is the case. Now things become a bit more tricky. So if I have average degree 3, so the output of my algorithm is, telling me here 1.01 or better as approximation ratio, which is not too bad. So usually it's with several zeros between the 1 and the first non-zero digit. I should say some more here. Namely, how did we, or what does it mean if I say all factors of the algorithm could guarantee, that the argument could guarantee were less than something like that? Well, the funny thing is that the algorithm itself, and this is one of the beauties I would claim with this kind of rule-based approach, the algorithm itself can monitor itself somehow according to some kind of estimate of the current situation of the approximation ratio. What do I mean by this? If I look back at our example, so I did apply an exact rule, an exact rule, an exact rule. Well, all these were also exact rules. An exact rule. Now here there was one time an approximate rule and everything else was exact. I already mentioned this is off by 1. And of course the algorithm can keep track of this. So the algorithm itself knows I may not have the best solution here, but it's just off by 1. I can just count this. And therefore I can also compute my personal approximation ratio. It doesn't say that this is not the optimum solution. I mean, I cannot rule out this, at least not in poly time, yes. But for, I think, many practical circumstances, it's perfect if the algorithm not just says, okay, I have implemented a 1.5 approximation. Recall this. I mean, this was the theoretical result, is 1.5. But the algorithm themselves can tell, okay, no, I'm doing far better. And I can show you. I have a proof for that. Just by running my algorithm. And, well, if you go a bit further, so average should be 3.5. It's something like 1.05. And if I mean this all, so really, we ran thousands of experiments, as I said. And never, ever, it was worse than this. And often far better. So this is just giving really the upper bound experimentally of this. And same with this average before. So we proved 1.5 in the general case. That's our proof. But experiments have 1.1 or better. So, and of course, you can also keep track of many other things. For instance, we have something like 20 reduction rules. As often, I only showed you some of them. But in the end of the day, we use them for our proofs. And we can construct graphs where they must be applied, but sort of randomly they never occur. So we really have some reduction rules which are never, ever applied. Okay, it happens. Okay. Okay, we got a bit more bold. We know that our algorithm works for average degree 4. That's what we proved. But what if we scale up a bit? So what if we run this on graphs of higher average degree? Well, we have no guarantee for that. But nonetheless, if we throw in graphs of average degree at least 8 so we can completely solve them, it means that we still have this upper bound of 1.5. So that's kind of what we started having as a boundary condition. And well, one more thing, maybe not surprising, the approximation factor gradually really increases with increasing average degree. So I don't have this very good approximation factors afterwards, but still far better than 2, say. And I at least think that this might be also very nice to combine with server exact algorithms finally. So if, I mean, all this, I mean, if you throw at your favorite laptop computer, we didn't had any fancy hardware, just laptop computer. So if you throw something like 100, 200,000 node graphs to them, they will solve it in 5 seconds at most or something like that. So this is nothing very complicated. And of course, that might be also nice to combine with exact algorithms for server purposes. Be it trying to cut off branches of your recursion tree, for instance. I mean, if you know that you already have a solution that uses this many nodes, then it might be not useful to pursue a certain path because that will be a worse solution anyways. So something like that. So I'm pretty sure that you can get out of this much more than I did tell you here. Yep.
I think what you get is small enough that it's possible that you could use it for the input to some iterative compression algorithm.
Sorry?
You could use something like this as the input to an iterative compression algorithm, or is what you're talking about?
No.
Too big for that.
Well, that might be also possible. No, I was just thinking about, well, what do you do? How do you solve vertex cover? Maybe some branching algorithm, some start kind of that. And I mean, if you want to do it exactly. Yeah. And first of all, as I said, this was coming out of a paper which was actually doing parameterized approximation. So of course, you can try to combine something with that. That's pretty easy to do. And secondly, even if you are really after exact solutions, knowing a solution where you know that's a factor 1.005 of the optimum, you basically know the optimum. So that allows you to radically cut search paths. If you are knowing, okay, this path will never be better, things like that. So therefore, go to the next one. And that should help speed up this type of algorithm for sure. I mean, we did not do this, but I'm just very confident that this would help also with processing of getting exact solutions, not just approximate ones. Just because there comes this guarantee of an approximation ratio. This be a really important bit, which is far better than these theoretical guarantees. And still, this is all very fast. Okay, maybe I should turn to theory again a bit. So there are basically 2 papers to be mentioned that deal with bounded average degree graphs before, and also the bounded degree graphs like these 2, where this Beermann-Fujito paper has some funny drawbacks, I must say. We try to implement that, and this epsilon that comes into play there is not that small in practice. So in the end of the day, Hochbaum is kind of to be preferred here. Yeah, so the current, the up to then point record was this one from Aldous and Radhakrishnan, and from 97, as far as I know, at least. Although I think that this bounded average degree thing should be really more prominent in the literature. So maybe this is hopefully a bit inspiring to go more into that for other problems. Okay, let me wrap up a bit. First of all, this rule-based approach, as I call it, I think it's really easy to implement. I mean, as I said, this was a bachelor kind of thesis, and I mean, you just have these simple pre-processing rules. Basically, every computer science student should be able to do it. Furthermore, this bank business, I think, is really something which is a kind of cute idea which I haven't seen before anywhere else. You may prove me wrong, but I already told you about the possibility to combine this with other exact approaches. But as I said, so the main point here is really that this algorithm itself can monitor somehow its approximation factor. And knowing this, we can, of course, do many other things. For instance, we might have some kind of trade-offs between precision and running time. If I want to have my solution reasonably quickly, but again, I'm also happy to spend this time getting better solutions. So I can just scale it a bit and invest more time when I know, okay, here my approximation factor is not that. I mean, finally, graphs will be split into components. That also happens often enough. And you can do this separately on the components as well, of course. And if you know that on a certain component, this algorithm is not doing well, okay, then throw it to some exact algorithm or something like that. So just to play with it. Of course, you can come back to things like FPT approximation. And because I think at least some of you might have hoped or expected that I talk about FPT kernelization, or sorry, FPT approximation. So just to point you to this lossy kernelization paper where basically Daniel and many of his colleagues, Sackett and so forth, worked out a nice theory to embed basically approximation within the idea of kernelization, and including lower bound techniques and so forth. Another thing I mentioned in my talk was this local ratio technique. I didn't really go into details there, but I want to mention at least that local ratio, as basically any other of these typical traditional approximation techniques, allows you to deal with weights pretty easily. Weights are not so much, or have not been so much on the agenda of FPT. For several reasons, I think. I mean, the most prominent being, if you really parameterize by the weights, so you always have to assume these weights are at least 1 or something like that, which seems like a technicality at the first place. But if you look at the local ratio arguments, they always play around with reducing the weights a little bit everywhere, something like that. And this is dead for FPT. So this is definitely not the same thing. But it may be that we FPT guys simply looked into wrong parameterizations there. I don't know whether you're aware of this paper of Hadas and Meravi, pretty recent JCSS. So they basically parameterized with a number of vertices, say, in the solution set, not by their weight. And in many cases, the weighted case becomes as hard or easy to solve as the unweighted thing then. So, and in particular, because this parameter is sort of smaller, say, in general, than the idea of taking the weight, or the sum of the weights or whatever, as a parameter, this is really maybe the real way to go, and also to be able to combine this with other approximation techniques. Okay, having said this, what I wanted to emphasize once more is that this local ratio technique finally gives you also this local transformation rules, which is some other name for reduction rules. So we have, in the end of the day, similar things happening there. But what I didn't see so far in that area is this kind of self-monitoring that I try to highlight with our algorithm. And the point being that probably those guys, put it this way, I'm not trying to harm them in any way, but are not really interested in rules, for instance, that are exact, say. Well, they only have this one single rule which is approximative and that keeps getting down there, the size of their instance and doing everything well in terms of local ratio. But just to combine this with exact rules in order to say, okay, sometimes I can do better and I can monitor this. And finally say, okay, the algorithm really does better than it should do in theory. That may be something on top that should be added just in order to have some more practical algorithms in that type as well. I should also mention once more that Some of the classical techniques in approximation, like primal dual methods and stuff like that, can be interpreted, not straightforwardly, but can be interpreted in a combinatorial way, which means that, or in my regard, that means that this local ratio thingies apply again, which means again they are finally some kind of reduction rule-based thingies, which is kind of cute, because at least I understand much better than how things work. And again, I could then also implement these self-monitoring features and all this. So, of course, I should also iterate here and repeat that these implementations and practical comparisons of algorithms should be really useful and should be done. I mean, this is one of the downsides of many of these theory works, that they never get implemented, but this is not just a problem with sort of exact algorithm, but also with approximation algorithms, so far as I can see. So there's very few experimental papers in this area, surprisingly maybe. And as I already told by the question, or due to the question of Kate, so combining these self-monitoring approximation thingies with exact methods should be really helpful to cut down trees and have exact algorithms run better in practice. And, well, to really have the final say here, so to speak, maybe my whole mini course was a bit bold in the sense that, as I mentioned in the very beginning, approximation did predate FPT by decades. So, of course, FPT should also profit from all that has been developed for approximation. And just to mention one paper where they did a very nice job in trying to get some LP thingies work for FPT. So, of course, there's this other direction. And, of course, maybe approximation has much more to offer, actually, to some extent, because of a longer history. So we should go into that direction, of course, as well. So we as FPT guys say. But I think we have now come to a point where we can have a rather fruitful interchange of ideas and see how we can really go together in order to get better algorithms in practice and also to understand heuristics better. I mean, this is the other thing that is always the main point for selling kernelization algorithms. And it seems to apply in a similar spirit also for many, many of these approximation algorithms, if you read them this way. Okay, so let me stop here. Thanks for your attention. And of course, I'm happy to take your questions now. Questions, comments, remarks, results?
It was very useful. I agree with your observations for that.
Okay. Thanks.
Yeah.
Yeah.
Oh, sorry, was it?
Yeah.
Yeah. So I have this is probably a stupid question.
No, there are no stupid questions.
Yeah, well, maybe wait till you hear it. Okay, so like the stuff I do is typically, it's just decision problems, and it's decision problems that aren't trying to optimize. It's really just straight yes or no, right? Is this the unknown? Is this the three sphere of these two manifolds?
Yeah.
And one of the things I've never looked at is approximation algorithms, because I just have no idea how to, like, do you know of any way that these kind of things that give approximate but not exact guarantees can be used for problems that aren't trying to minimize or maximize, or yeah, maybe it's a really stupid question.
Well,
There's all these techniques, right?
Yeah.
Wonderful type of techniques. It'd be nice to be able to steal.
I don't know whether it makes sense to ask some kind of optimization problems or questions as well. I mean, if you're, okay, you are interested into this unknot problem, say, but maybe to some extent, it might be also interesting to minimize the number of crossings, or however that's called in your world. I mean, of course, crossing 0 would be then something like the unknot, but isn't this the minimization problem behind in that case?
So crossing, okay, so the answer makes sense. So crossing number is enormously hard to compute, but
Yeah, okay.
no, sure, but there are other invariants like like degree of, I don't know, like the genus,
Yeah, okay, yeah.
yeah. So, yeah, sure.
Mm.
Which all have to be at least as hard as unknot recognition, because unknot recognition is
Sure, that's unfortunate, yes. It's not a trivial thing. I mean, in many cases, the smallest possible values, like 0, are trivial to find in these kind of examples, and this is not the case in your case. So, yeah.
Okay.
Sorry, yeah.
I was